today we're going to talk about this great result of Pfefferman-Einstein, or maybe just a Pfefferman, which is the H1 BMO duality. So we want to show that basically that this is what we're looking for. We want to show that that the linear functionals on H1, any continuous linear functional on H1 can be realized as integration against a BMO function. And so roughly speaking, and backwards, that any BMO function, if you integrate against it, then it gives rise to a continuous linear functional on H1. This is not exactly right, as you know from in the book. Finally, you've noticed there's this comment that Mark, it's not true that the integral of an H1 function against a BMO function always converges. Okay, so this is not exactly what I just said is not exactly true. Okay, but to a certain extent, it is true. So let's make it precise. So we're going to use a bit of notation. Let H10 denote the dense subspace of H1 consisting of finite linear combinations of atoms. Okay, so this is a dense subspace. See, all these guys are bounded and are compactly supported. And then, like I said, our theorem is going to be that given any G in BMO, then L sub G, right, which is this, which we defined a long time ago, just as integration against G, turns out to be a initially defined on H10 has a unique extension to all of H1 and satisfying the such that the norm of this linear functional is controlled by some constant times the BMO norm times the BMO norm of G. Okay, so you start off with what is true is that you can start off with a BMO function, and then you create a linear functional on H10. Okay, you create a linear functional on a dense subspace. So this will work for even, this works for any function in BMO. And you can create a linear functional on this dense subspace because, right, the integral is always going to converge if you're integrating this BMO function against a compactly supported bounded function, right? So you don't have to worry about convergence. So you initially define it on here, and show that it satisfies shows that it satisfies the norm condition, and then use the fact that H10 is dense in H1R to extend it to all of H1. Okay, so it's in that sense that that BMO can be realized as H1 star. And conversely, given any L in H1 star, there exists a G BMO such that L is LG and the BMO norm of that guy is controlled by the H1 star norm of L. So it is in this sense that H1 star can be identified with BMO. Any questions? So this is one of the results of the 1972 paper of Beckerman and Stein. And Stein, in his big book, says that it's due to Beckerman by himself. It's difficult to call the Beckerman-Stein duality. I don't know how old Charles Beckerman was in 1972. Maybe he was 17 years. No, I should probably figure out how old he was then. Anyway, he was pretty young. Okay. So let's do part one. So proof part one. So we want to show that this LG, right? We want to take G BMO, and we create this LG, and we want to show that this LG has the right norm as a linear functional. Okay, so we want to show that alpha G is defined and bounded on H10, right? Bounded as over there. So you see that it suffices to obtain the inequality, to obtain this inequality, that this is controlled by some constant times the BMO norm of G times the H1 norm of F. Right? I mean, we're basically saying the same thing. Right? This is LG F. Suffices to show that we have this, because that's exactly what we're looking for. Okay. So, so we want to control the integral of this function against H1 functions. Okay. So we'll do it in steps. Case one. Let's assume that G is in L infinity. Okay. F is in H1. So F has an atomic decomposition. Right? That's going to be our big tool. That is our tool, or actually it's our definition. We have an atomic decomposition. And this converges, as you recall, the right-hand side converges in L1 to F. So if we look at this, we can realize it as this because of that convergence. So we just use an atomic decomposition first, and then so let piece of thing be a ball on which A sub k is supported. Right. So we're trying to slide in the BMO norm on the right hand side. So and let G sub B k be the average, right? So be the average of G on B sub k. So the move is obvious, right? The move we're going to make is obvious. These guys have tessellation, so we're allowed to slide in whatever constant we feel like. So we slide in the mean. Okay, and then we use. So this is integrated over B sub k, right? A sub k, each A sub k is supported on B sub k, so I'm just going to put the B sub k in the integral. And now we use the other fact about A sub k. We know that the infinity norm of A sub k is controlled by 1 over the measure of B sub k. And so this is starting to look, this is starting to look pretty good. So we see that, so we get that the absolute value of this of the integral of g is controlled by the sum of the absolute values of the lambdas, 1 over m b sub k, g minus g b sub k. Right? Because we can replace A sub k by its own infinity norm, namely 1 over the measure of B sub k. Okay. But then you see what's going on. Right? What's this thing? Right? This thing is controlled by the BMO constant of g. Right? So you get this is controlled by the BMO constant, and you get this thing, right? And then you play the usual thing. You take the infimums over all atomic decompositions, right? Infimums over all atomic decompositions. And you get that this thing is controlled by exactly the BMO norm of G against the H1 norm of F. Any questions? Please straightforward. Okay. Case 2, for the general G in BMO, right? So previously we were assuming that we just did it for G in infinity. Now let's do it for G in BMO, and you do it by approximation. So let's just assume that G is real value for simplicity, and let G sub k, G super k be, well, it'll be equal to k if G of x exceeds k. Oops. G of x exceeds k. It'll be G of x. Well, it'll be negative k if G is lower than negative k, and it'll be G otherwise. So you have some function, right? You have some function, and you fix k, right? It's negative k, and you create the truncated function by chopping it off at height k. Right? So you just create an L infinity function. You create a new L infinity function that is equal to G, whatever G is in magnitude smaller than k. And then you approximate. You say, well, then one can see that it's possible to see that the BMO norm of this guy is controlled by some constant times the BMO norm of the original. So by case 1, we know that the integral of f against gk is controlled by that constant. That's the BMO norm of f. And then the gk go to g almost everywhere, right? And f is bounded and of compact support. Compact support, right? So that gives you that f gk converges, I'm sorry, the integral of the f gk becomes the integral of fg by dominated convergence. By the dominated convergence theorem, this thing on the left converges to the integral of fg, and then you're done. Okay, the backwards direction, okay, so the other direction showing that given any linear functional, we can create a BMO function that G, so that L sub G is that linear functional. Is kind of a cool trick that you will probably have to use in an upcoming homework. So, okay, so it's going to be 2.2. So, let L be a linear functional, right? Let L be a linear functional on H1. Okay. And just for convenience, let's introduce some notation. For each ball B, for each ball B, let L2 sub B be the square integrable functions. Square integrable functions on B. So just L2 restricted to B, right, with the L2B norm being the 1 over the measure. I'm sorry, excuse me. Being the L2 norm of the function. Oops. That should be enough. Sorry. It doesn't matter. Okay. So it's just L2 functions on the ball and the L2 norm on the ball. Okay. And then let L2 be 0 be the L2 functions and then L2b such that the integral is 0. So that they satisfy cancellation condition. Right. So they would be that'd be an L2 function supported on the ball, right, and satisfying the cancellation condition. Right. So it's very close. These guys are very close to being atoms, right? As long as notice that as long as the L2 norm of the guy, right? As long as the L2 norm of the guy is controlled by 1 over the square root of the measure of the ball. So notice that if this happens, then F is a 2 atom. F is a 2 atom. Right? These guys are basically 2 atoms. If they're the right size, then they are 2 atoms. Right? That is to say, like, if you take any function, right? That is, for any f in L2 be 0, 1 over mb square root times the L2b norm f is a 2 atom. This is a 2 atom, and so we know that given so for any such f, we know that the H1 norm of that f, right, is controlled by some constant times this. We saw earlier that that our 2 atoms all had the 2 atoms all had H1 norm bounded by some constant. So this is saying that's all we're saying. Okay, so anybody in L2b has an H1 norm that's controlled by its L2b norm as the measure of the square root of the measure of the ball. Okay. So now comes the fun part. You say, well, okay, let's look at. So now consider L. Right? We have this linear functional on H1R. Let's consider L. And let's assume it has norm less than or equal to 1. Let's consider L restricted to L2B. Okay, we're going to consider its action on L2B. And what you see, of course, is that LF then is bounded by the H1 norm of F, right? Because it's because it has norm 1. Right? It has norm 1. But we just saw that the H1 norm of F is controlled by some constant times the square root of the measure of the ball times the L2B norm. Okay. So what that tells you is that L is then a continuous linear functional on L2B. And you can think of it as a continuous functional on L2B. Right? And because of that, you know that, so we know there exists some function g sub b in L2B such that for all those guys, LF equals the integral of f against g super b for all f in L2B, L2B, comma 0, sorry, should be a 0. And such that the L2B norm of this guy is less than this constant times the measure of the because you know the norm of L as a member of L2B star is this. It's controller. Okay. So this is pretty good, right? What we have is that for each ball, if we look at each ball, then we have a function that works for that ball, basically. We have a function that we integrate against that works for that ball. Okay. Okay, so now observe that whenever you have one ball contained inside another ball, then G super B1 and G super B2 yield the same linear functional. On L2B10. And that implies that they must differ by a constant. GB1 minus GB2 is some constant on B1. Because you're integrating these guys against functions with integral 0, right? So, if they're the same, then if it's the same linear functional, you must differ by some constant. Okay. So this is the part that I'm a little bit uncertain about, actually. So I want you to think about it. I have a way of explaining it, but I'd like you to think about it for a bit. So at this point, the argument goes like this: replace G super B by G total B, which is G super B plus some constant, where C sub B is chosen so that the integral of G super B twiddle is 0 over the unit ball. Okay, and then it says whenever B1 is contained to B2, we have G super B1 twiddle equals G twiddle B2. Right, and we can define G of x consistently. Over all of R B. Okay, so I'd like you to think about that. Does that bother? Is there anything that bothers you about that? I'm not saying that it's necessarily wrong, but does that seem okay to you? So I'll go outside and talk to each other. Does that make sense to people? If it does, please explain it to me. Right, so right now what we have is that on each ball, right, for each ball we have this G super B, right? B1, B2, that's G super B is on each of these balls, right? And we know that if one ball contains another, right? If one ball contains another, then they must differ by some constant. Okay, so you can, in that case, you can, subtract off the constant from one of the guys and make them agree on the lower ball. Okay, so what they're saying is that, well, let's add on constants so that whenever we integrate the guy, so suppose here's the unit ball over here. So here's the unit ball over here. Subtract off a constant so that the integral of that guy over the unit ball is always 0. Okay? And then, so this is the part that's really, then we have that whenever you have balls containing each other, they're going to agree on the inside ball. Does that seem reasonable? Doesn't seem reasonable to me. It seems like there's something that they're wrong. Right? Does that follow? So my problem is with this then. I'm wondering, did that bother anybody else? Okay, so just thinking for a second, like if you had two balls that intersected, right? If you had two balls that intersected, say D1 and D2. Right, you'd know that, well, I mean, you could put a ball inside here, and you'd know that you can subtract off a constant. You can subtract off a constant so that the upper guy agrees with this guy, and the upper guy over here agrees with this guy. So agrees on that ball. They would agree on that ball. So. Yeah.
What is the unit ball doing?
The unit bar, I think, the way I think of the unit ball is that it's sort of like a seed, you know, like you're setting your constant, you're fixing your constant at some point. So what I'm thinking rather is that what you do is that for GBU, you know, normalize it, right? So subtract off, replace it by G little bu, so that the integral of that guy is 0. Right? So you have to set some level first. Right? That makes sense to me. Right? You have to set some level, and then you make everybody else agree with that. You make everybody else agree with that. So, right. So maybe you sort of seed. You fix a height for one of the guys, and then you align everybody else with that guy. Right. So then after that, whenever you have a ball, then for any B containing BU, right? Again, you normalize. You subtract off, adjust G sub B so that G sub B restricted to B sub U agrees with G, so that the new guy agrees with the guy that we fixed. but then are you guaranteed that whenever you have a ball containing another ball, that it's going to agree on the interior, on the lower ball? Okay, so that I don't know if you have any ideas about it, but that step seems a little bit. I'm not that step bothers me a little bit. Okay, so I'm gonna let me think if I can make it a little bit if I can make it a bit more precise, or maybe I'll go and read the original paper to see what's going on. But something is fine there. Okay. In any case, let's suppose that one actually can do that, right? So then by some argument you can define G. You can define G in a way that's consistent for every ball. So right, you can take one can take G of x as G twiddle x for any ball containing x. Okay. Okay. So so then right, so that gives us our G, and what we want to do is control the BMO norm of G. So we say, well, look, we control the BMO norm of G. Let's consider the integral of 1 over, the average of G minus CB. So by Cauchy-Schwarz, we know that this is controlled by, where CB is the constant that we added on over here. CB is this constant. We know that this is controlled by Cauchy-Schwarz. We know that this is controlled by the L2 norm of this times the times the constant 1, and we G minus CB on B is just our old G super B. Our G super B is from over here. Right? You subtract CB off from G total B, you know, G super B. Okay. But now recall that recall how we got the G super B's. They were the guys we had some control on the L2 norms, right? The L2 norms were all controlled by some constant times the square root of the measured ball, right? Because L sub G was L sub G had L, because L had norm 1 on H1, which implied that it had norm C square root of B, square root of the size of B on L2. Right? That was that at the very beginning, that you have this guy on H1, and if you restrict it to L2, it turns out to also be a linear functional. Its norm turned out to be c times the square root of the measure of b, right? And so you got that L arose as integration against some function g, whose L2 norm was controlled by that. Okay. Oops. Now we're good. And so what we get is some constant. So we get some constant, and so that which is good, right? Because we wanted to show that the BMO norm was controlled by some constant times the H1 star norm of L. And we assume the H1 star norm of L is 1. Right? So thus the BMO norm G is controlled by some constant times the H1 star norm. Right? We normalized at the very beginning to make this 1. So getting this bounded by some constant doesn't help us. So thus, LF equaling fx gx holds for all f in L2 B naught, and thus for all f in H01. And so that gives you the representation. Okay. So barring something that is a little bit that I'm not completely sure, that I'm not exactly sure of, and that's basically the proof. Okay. So, any questions outside of the part that I don't know the answer to? Does anyone have any questions? Yeah, William.
Can you summarize again why GP1 minus GP2 has to be a constant number 1?
Okay. So these guys are the same linear functional, right? These guys. You're integrating, as I say, integrating some function against B1 is going to be integrating the function against B2. Okay, for all f in L2 B equals 0, right? If you integrate against GB1, you're going to get the integral of that function against GB2. Okay. So these guys are going to differ by some constants. Remember that the f's satisfy the cancellation. Okay. So this is only going to happen. This could only happen if these things differ by some constant. Okay, so that is finally the end of chapter 2. That's the end of chapter 2. So now we're going to return to more so that chapter was more along the lines of applications of functional analysis. And now we're going to return to application of the ideas that were introduced in chapter 1. Now we're going to introduce some more ideas and see their applications. Okay. So chapter 3 about distributions, also called generalized functions. By the Russians. I think generally people in the US call it distributions, but you could call them generalized functions if you want to seem eccentric. So, okay. So this is sort of a shift of point of view of what a function is. Okay. From the point of view of distributions, a function is something that you integrate against. Okay, so what is a function? What is a function, right? It's no longer something that takes in a value and spits out a value. Right? It's no longer something that assigns a value to every point on the line. Right? Rather, you think like this: one determines a function, or a function is determined. Say, by the quantities, the function f say, is determined by the quantities f that you get when you integrate the function against other functions. Okay, where the phi range over a class of what are called test functions. Okay. So if you have a function, if you have some guy, and whenever you integrate it against these other guys, right? Suppose you have two things, right? You have g, and whenever you integrate it against the test functions, and you let for over every single test function you get the same answer, then basically you consider these things to be the same thing. Then you consider f and g to be the same thing. Okay. So you consider functions to be linear functionals on the space of test functions. Okay. So instead of thinking of functions, you think I'm going to have this class of test functions, and I'm going to look at the linear functionals on that class of test functions, and that's those are my new concept of what a function is. Okay. Okay. So let's introduce some notation. You have omega and d. C0 infinity omega. Okay, so the compactly supported, infinitely smooth functions on omega. Okay, you might ask, why don't we just say C infinity omega? That's a good question. We don't. Okay, for some reason in the world, whenever you talk about distributions, you always use this P. So that's why this is not a definition, it's just local notation. Okay. So infinitely differentiable functions of compact support on omega, it's called B. And this is going to be our class of test functions. Okay. So okay. Now I'm going to introduce a very weird definition, and it will not satisfy you. Given a bunch of guys in B, if the supports of the phi sub n are all contained in a common compact set, and 2, for each multi-index alpha, p sub x alpha, p sub n converges to d sub x alpha phi. I'm sorry, I should have put in phi here also. So given a sequence p sub n, a function phi, and the phi sub n are all in d omega. So if for every multi-index the derivatives converge, the derivatives of the phi sub n converge to the derivative of phi uniformly in x, then we say that phi sub n converges to phi in d omega. Right. So this is the definition of convergence in d omega. Okay. So does this seem a little bit strange to you? What's strange about this? How do you normally define convergence? How have you defined convergence in the past? Well, like if you go back to like 131 or something, then you have some metric, right? You have some metric, and you say that given any epsilon, if there's some if you can make these guys get close to this thing, then we say converges to it, right? But there's no metric here. There's no metric here, and you might be wondering, can one? Are we going to get a metric? And the answer is no. Okay, the answer is no. That so there's an alternate way of defining this sort of convergence using the topology. Okay, so there's using a topology, but it turns out that topology is non-metrizable. Okay, so it's you actually cannot get a metric with respect to which this sense of convergence can be defined. So Stein is, as usual, being very practical and saying, no, I'm just going to ignore, instead of talking about the topology, I'm just going to ignore the topology and just talk about what convergence means. Okay. If you want to see the topology, and this was one route that I considered taking in this course, but it would be sort of like a huge detour. If you want to see that topology, go look in Rudin's functional analysis. On page 153, theorem 65. But having gone that route myself, when I first learned functional analysis, I think this is a good choice because learning about the topology is quite involved. It's quite involved. I almost feel like as a child of immigrants, I've never really mastered the art of swearing in English, but thinking that one can sort of go around all that trouble and just go this way instead. Makes me feel like I wish I had mastered it. Okay, so now we're going to do something also strange. That'll seem also, so we're going to do something again that is very pragmatic, but sort of mathematically bizarre. Let f be a function, a complex value function on the space of smooth compactly supported functions. Let this be a linear function. If this guy is continuous with respect to the above notion of convergence, that is to say that whenever p sub n converges to p in the above sense, we have f of p sub n converging to f of p as in the sense of complex numbers. Then we say f is a distribution. On omega and right f. We say that f is in D star. D star. So, as before, we're sort of avoiding, we're circumventing topology here. Right? Normally, what you want to do is define the topology first, right? And say, okay, with respect to this topology, we have some notion of convergence. With respect to the topology, we have some notion of continuity, right? And you say, if the function is continuous with respect to the topology, then you call it a distribution. But what we're doing is sort of a backwards way. We're saying, okay, we're going to define the convergence and say that the function is continuous with respect to the notion of convergence. Okay. And as long as it is, then we call it a distribution. But I just want to stress that it can, and maybe in some sense should be done the other way as well. That is, you actually can define a topology and say we've got convergence, and we've got if you have a continuous linear functional, then you call it a distribution. Okay. But effectively, this works. So fine, to reduce the amount of material we need to do. Okay. So So just for a simple example, so for example, integration against the Dirac delta function is a distribution. If you, the Dirac delta function, of course, you integrate against the Dirac delta at 0. Right? You integrate some function against the Dirac delta at 0. That's going to pick up the value of the function at 0. Okay, so that picks up the value at 0. And if you have, if you have a bunch of functions, you have a bunch of smooth functions that converge uniformly to something, well, the Dirac delta is going to respect that, right? So the Dirac delta, evaluated, the functions evaluated at 0 are going to converge to the value of phi at 0. So this, so the Dirac delta function can be considered a distribution. The Dirac delta function is a distribution. So one sort of doesn't distinguish, one sort of conflates the thing that you're integrating against and the operation of integrating against it. So we consider the Dirac delta function to be a distribution. It determines this distribution of integrating against the Dirac delta. You consider those two things to be the same. Okay. And in fact, in general, integrating against Borel measures, any Borel measure that's is finite on compact sets, subsets of F, subsets of omega, is still going to be a distribution. Okay, let me try to get at least one more idea in here. Okay, so derivatives of distributions. Okay, so so think if you have some function, right? If f is smooth and phi is in d omega, then we have that if we integrate the derivative of f against omega, well, by integration by parts, you're going to get the integral of f against the integral of f against the derivative of the function. Right. So considering this in right in distribution language, right? This is integration against this partial, right? Integration against this partial is the same thing as integrating the partial against f, and that's a constant. Okay, so we define for any distribution the derivative. We define the derivative of that distribution. Right? We say the derivative of the distribution is that guy that's going to take a test function. What will its value be? What will its value be on the test function? Its value of the test function will be -1 to the alpha, to the size of alpha, times f of the partial times the derivative of the test function. So the distribution is this linear functional, right? The distribution is this linear functional. And you say, okay, how are we going to define the derivative of this guy? We'll define it to be the linear functional that is defined by taking the original linear functional against the derivative of the test function times this constant. Right? In accordance with the above, in accordance with this thing here, which is true for functions. Okay, so we extend what happens for functions to all distributions. Okay. And what this says is that every distribution is infinitely differentiable. In this sense, every distribution is infinitely differentiable because to differentiate basically involves applying the original guy to the derivative of the test functions, and the test functions are infinitely differentiable. Okay. So let me just do one simple example, and then I'll let you go. If you have the Heaviside function, the Heaviside function is basically the characteristic function of 0 to infinity, right? So it says off, on, right? It turns on. It's just something that says on at some point. Then, for all phi in B, for all phi in the test class, well, what's the derivative? Oops. What's the derivative of this function? Well, the way the derivative is going to act on the test function is going to be just the Heaviside function, -1 to 1 times the Heaviside function acting on the derivative of the function. Okay. So the Heaviside function as a distribution acting on this thing. Well, that's to say you're going to have the Heaviside function integrated against the derivative. Right? That is, -1, Heaviside function is just a characteristic function from 0 to infinity of the interval from 0 to infinity. Right? And so you end up with phi of 0. So the way that the derivative of the Heaviside function acts on the test functions is it just evaluates the function at 0. That is to say, it's the Dirac function. It agrees with the Dirac function as a distribution. So the derivative, in the sense of distributions, the Heaviside function, the derivative of the Heaviside function is the Dirac delta function. Okay. So next time we'll talk more